Hello, everybody. I am Ajay Singh, your TA for CS798, and welcome to this lecture presentation on an alternative way of reclaiming memory in concurrent programs, which is a safe memory reclamation algorithm, which we call neutralization-based reclamation. This is a work done under the supervision of Professor Trevor Brown in Multico Lab and Professor Ali Mashtizadeh in RCS Lab in University of Waterloo. This work was recently published in PPOP 2021, where it was amongst top 4 manuscripts, and it also won Best Artifact Award at PPOP. So before we begin, let me introduce you to Mr. Concurrent Programmer, whose services we would be using throughout the presentation. He has developed a simple, fast, linked list data structure, which is popularly known as lazy list. And we'll use this data structure as an application to understand various concepts in the presentation. So before we start upon, let's do a quick review on what is a lazy list and how it is designed. So we'll see that through the pseudocode. So lazy list is this data structure where it has insert, delete, and contains operation, and each operation has a synchronization-free search and to find the desired location where the operation needs to take effect, and then the desired location, which is in terms of predecessor and current nodes, they are logged and they are validated, and then the operation takes place. So let's see the first operation, insert. So this insert operation has a synchronization-free search where the desired pred and current nodes are found where the key would be inserted. And once this search returns, if the it will return predecessor and current nodes, and if the current node has the key which insert is trying to add, then it will simply return false. Otherwise, if the key is not already present, then the predecessor and current node would be logged, and they would be validated to ensure that the predecessor and current node haven't changed, since the synchronization-free search returned them by any other concurrent update. And so that happens in the write phase. You can call a write or update section of the operation. So the validate is actually the simple process, the simple instruction where you validate whether pred and current nodes are not marked, and pred still points to the next. So that implies that since the time synchronization-free search returned these nodes, they haven't been changed. And if that is the case, that means the validation succeeds. Then insert could simply go ahead and add the node between the pred and current nodes. And before returning, it will unlock these nodes, and the operation would be a success. Similarly, delete also has a synchronization-free search where it returns the target location in terms of predecessor and current node. And if the key is already present in the current current node, then the delete operation returns false because the node it is trying to delete is already is not there. And if the key is there, it locks the predecessor and current nodes and again validates in a similar way, and then moves ahead to mark the current node, and then swing the predecessor's pointer to the currents next. So note that this data structure, which Mr. Concurrent Programmer has designed, doesn't have reclamation. So we do not free the current node. And then before returning, the delete operation unlocks these nodes and moves ahead. Similarly, contains also does the synchronization-free search. And once it reaches the node which contains the key, and if the node is not marked, it will return true, otherwise it returns false. So this was an overview of simple lazy list data structure, which Mr. Concurrent Programmer has developed. I'm using Mr. Concurrent Programmer but as a reference, but this is a very popular and amongst simplest data structures in concurrent programming world. So Mr. Concurrent Programmer, after designing such a data structure, decides to execute it on his system, and he finds that the memory consumption of his data structure is very high on the system. So in fact, this plot, the x-axis shows the time passing, while the lazy list is executing, and the y-axis shows the memory consumption of the system while the list is executing. So you can see from the trend that if the lazy list executes for long enough, at one point it will exhaust this underlying system's memory. So this has a repercussion. That means without any reclamation, it's impossible to design dynamic size data structures. So Mr. Concurrent Programmer realizes this and decides to add reclamation capability to his data structure. But unfortunately, his understanding of reclaiming memory in concurrent programs actually, since he's trained in a sequential programming world, so his idea of reclaiming nodes in a concurrent program comes from the sequential world, where the life cycle of a node is thought of as follows. So initially, a node is in unallocated state, and when it is assigned memory, it enters into the allocated state, and when the node, after being allocated, is inserted into the data structure, it becomes reachable from the head or the root of the data structure, and finally, when it is deleted or unlinked, the node can be freed. So this is a life cycle of a record in a sequential world, and this is what Mr. Concurrent Programmer thinks in mind while he wants to add reclamation to his data structure. So with this life cycle in his mind, Mr. Concurrent Programmer simply adds free after unlinking the node in his delete operation, and thinks that now he is done and his program should work correctly. But there is a problem in this way of freeing the memory. Let's see through an example. When he executes the data structure in a system, what could go wrong? So assume this lazy list, this short lazy list, and a thread T1 trying to find or execute contains node N3 on the list, and a thread T2 is trying to delete node N2. Now let's say T1, while moving towards node N3, stops at node N2. While holding a pointer of the node N2, it sleeps. Simultaneously, let's say that T2 arrives, and to delete node N2, it reaches node N2 and has predecessor as N1 and current as N2, and then to delete N2, it marks it first, which is a typical lazy list way of doing deletion, and then swings the pointer of next of N1 to N3. Now, since he has added free in his delete operation, this thread T2 will free the node N2. Let's say later, thread T1 wakes up and tries to access this now freed node. What could go wrong? Well, you might have guessed, thread T1 would suffer a segmentation fault, or it would crash. And this happened because of use after free error. So the problem which Mr. Concurrent Programmer has just faced is formally known as the problem of safe memory reclamation in concurrent data structures. So let's see why it happened. So the problem occurred because some thread was holding a private pointer to the node N2 while it was being concurrently freed by another thread, right? So formally, this problem. This is called safe memory reclamation problem, and it is this challenge of deciding when is it safe to free a record in a concurrent program. Well, so a simple solution could be that do not free a node or a record unless it can be proven that it is safe to free, or unless it can be proven that no thread would be holding a private pointer to this node, or in other words, unless it can be proven that use after free hazard cannot occur. So in fact, most of the solutions in state of the art have this observation at its core, and they require threads to arrive at the consensus that whenever a node is being freed, no other thread would be holding a private pointer, or all threads need to agree upon this fact that use after free hazard won't occur, so that the node is safe to be freed. So this implies that one cannot, after to delete a node in concurrent program, one cannot simply free it. Well, what needs to be done is that the node which is being deleted has to wait for the consensus to happen. So that means when you delete the node, it has to be saved in a temporary buffer, which usually typically in safe and reclamation algorithms is known as retired buffer or a limbo bag. So the record has to transition from reachable to the retired state, has to wait in that retired state until it can be proven that it is safe to be freed. And at that point, the record could transition to the free state, and from that point on, it could be returned to the operating system in unallocated state, where the node could again be reused. So this is the job of safe memory reclamation algorithm. So safe memory reclamation algorithm actually takes the unlinked or deleted node and then saves them into the local buffer or the limbo bag, and then tries to arrive at a consensus with other participating threads that use after free error could not occur, or no thread would be holding a private pointer. And if that's the case, then it can simply transition the nodes in its retired buffer from retired state to the free state. So it seems like all this extra work needed to safely reclaim memory in a concurrent program might have some repercussions. So it gives rise to, especially on the performance of the data structure. So it gives rise to certain questions, which are also can be thought of as desirable properties of any safe memory reclamation algorithm. So first of them is how much overhead would all this extra work will have on the data structure? Because if the same safe memory reclamation algorithm which realizes this consensus, or to decide upon a time when it is free to save a node, is very, very slow, then it would be a bottleneck on the data structure. So no matter how much you optimize your data structure for speed, but if you use slow safe memory reclamation algorithm with it, the overall data structure would be slow. And if the safe memory reclamation algorithm happens to be very, very slow, it would render the data structure impractical or perhaps unusable. Second question is, since SMR require to transition the data structure from reachable to the retired state, where they are temporarily stored until the consensus occurs, could it happen that the number of retired records grow unboundedly? Because if that, so that is referred as robustness of safe memory reclamation algorithms. And if the number of retired records could grow unboundedly, that would be equivalent to the case where we did not have any reclamation in the data structure. So it will again lead us to this problem where underlying systems memory might get exhausted. And the third important question from the programmer's point of view is how much programming effort would be required to add the safe memory reclamation algorithm into a data structure. Would it require any intrusive code changes? Would it require programmer to rethink about the correctness or progress guarantees of the data structure, which by the way are already complex things to do? And the fourth question is the applicability. How much general, how general is the safe memory reclamation algorithm is? So that it, or you can ask, does it apply to multiple data structures? So answer to all of these questions, the desirable properties depends on the way a safe memory reclamation algorithm designs its consensus mechanism. So let's see two classic safe memory reclamation algorithms which have totally different ways of arriving at this consensus to implement safe memory reclamation. So first of them is hazard pointers. So the way the consensus in hazard pointers is designed is that before any thread, before accessing a record in an operation, has to protect it. And any thread which is trying to free a record in an operation has to scan those protections so that it could skip freeing those records and free only the records which are not protected by any other threads. Because if a record is not protected by any thread, it implies that no thread holds a private pointer to that record, and it could be safely freed. So the API for the hazard pointers is simple. It just requires you to invoke protect on a record or a node which you want to access. And then when you are done accessing, node in an operation, you call an unprotect node function, and you use retire to transition nodes from reachable or unlinked node and then send it to the SMR to decide when it is safe to free. So the important thing is in hazard pointers is this protection mechanism, which is a three-step process. So first, every thread which executes a protect call on a node has to announce the node in a single item multi-reader location so that any other thread at the other end which is trying to free this node could first scan these reservations and then decide whether it is safe to free or not. And the second step in the protection mechanism is this fencing, which is required to make sure that announcements are not reordered with the scanning of the other threads. And the third step is this validation. So you need to validate that the node you announced was reachable at the time it was announced in the single item multi-reader location. And if you do not do this, if you do not validate the node that whether it was reachable in the data structure while you announced it, then it may so happen that you may announce a node which is just about to be freed. Right? So in that case, the protection would be useless and you may still crash. So these steps in this order are very important for protection to be correctly implemented in the hazard pointers. So now let's see how the hazard pointers could be used in a real data structure. So we will use update operation of the lazy list here. So as you can see, in the search phase of the lazy list, you do this protect, you do protect and unprotect calls in a hand over hand manner. So whenever you access a node, you protect it first, and then you dereference its next pointer, and then you unprotect the previous node, so that you just move in this hand over hand manner to the desired location. And once this while loop of the search phase ends, you have an invariant that the final present current nodes you arrive at would be protected, and thus you can safely go ahead and execute your update operation using those protected present current nodes. And once you are done with an operation, before you return, you can unprotect the nodes so that other thread which might be trying to free these nodes could free them. So now let's see what is impact of this way of implementing the consensus in hazard pointers on the desirable properties, which we saw in previous slides. So first, the speed. Well, so as you can see, since hazard pointers require every read to execute a protect call, and that protect call has a costly store and load fence. So because of this, hazard pointers are slow. So this overhead is per read. So reads also have this overhead in hazard pointers. And the good part in hazard pointers is that they are robust. That means since only limited number of records could be protected at a time, that means there is a bound on the number of records that could remain unreclaimed in retired buffer of any thread. Right? In fact, a thread could only protect, let's say, k number of records or nodes in an operation at a time, and n threads could do so at a time, right? So only k times n minus one records could be protected. That means they could only remain unclaimed. So there is this upper bound on number of records, which is k into n minus one, which could remain unreclaimed. So as far as usability of the hazard pointers is concerned, it's complex to use hazard pointers because in case the protection fails, one may require to rethink about the progress guarantees because the protection mechanism may fail infinitely many times. We'll see how in the next slide. And also, the implementation of protect function depends on the way data structure is designed, because protect call requires you to prove that that data structure was reachable while it that a node was reachable in the data structure when it was announced, So that means the condition of deciding whether a node is reachable or not depends on the way the data structure is designed. So it varies data structure to data structure. Now let's see the applicability. So this raises an important question whether hazard pointers applies to many data structure or not because of these concerns in usability. So let's see through an example of the lazy list again. So the way you implement protect call in lazy list is that you announce the node, the current node which you want to protect in a single item multi-liter location. In this case, it's a reservations array here. So you add the current node to the reservations array, and then you do an fence, and then you validate whether the current node is still reachable in the data structure or not. And the way you do is as follows: that you verify that pred node is still is not marked, and the pred's next still points to the current node. So this together means that current node, when it was announced, was still reachable. So that means you correctly protected the node. So now let's see an example of correct protection. So let's say a thread T1 has already protected node N1 and is about to access node N2. So it executes a protect call on the node N2. So pred is N1 and current is N2 in this case. So so the thread would announce the node N2 in its reservations array, that is a single item multi-liter location, and do an fence, and then verify that whether the node N2 is still reachable in the data structure or not. So it checks that pred is not marked and pred.next is still the N1.next is still the N2. So it returns true. So it successfully protects node N2 as well. Now, let's see a second example where node N1, which is protected, is marked. And now the thread is trying to protect the node N2. In this case, the third step of the protect call will fail because node N1 is marked. Because that means you cannot decide whether node N2, when it was announced, was reachable in the data structure or not. Right? So the protect call will fail. Now, the catch here is that when the typically in a data structure operation, when a protect call fails, that is handled by restarting the operation from the root or the head node of the data structure. So the catch here is that even though you restart this the operation, and next time when the protect call arrives at this location and tries to protect node N2 again, it might happen that the thread which marked the node N1 has crashed. So that means node N1 is still accessible in the data structure, but it is marked. Right? So the protect call will fail again. And this may keep on repeating infinitely if N1 is never unlinked from the data structure. So this has an impact on the progress guarantees of the data structure operation. Right? So that essentially means in any data structure operation where the sequence of logically deleted or marked nodes could be traversed, the hazard pointers do not apply because that would impair the progress guarantees of the data structure. So now let's move towards the next category of solutions, which has totally different way of arriving at a consensus, which is epoch-based reclamation. So in epoch-based reclamation algorithms, thread execute operations in epochs, which are logical timestamps. So each epoch has a corresponding retired buffer where any node that is retired goes into that corresponding buffer. And at beginning of each operation, each thread announces the epoch it is executing in, and also periodically tries to advance the epoch or increment the epoch so that reclamation could progress. And our epoch could only be advanced if all threads actually have arrived at a common epoch. So let's see through how the consensus is arrived in an epoch-based reclamation algorithm. So every thread periodically tries to advance an epoch, and it could only advance epoch if all the threads have arrived at a common epoch. So for example, if a thread is trying to increment to epoch E+1, it has to wait for all the other threads to announce the epoch E. That means all the threads need to be executing in epoch E so that some thread could advance to epoch E+1. Now, in doing so, when all the threads arrived at epoch E, that implies that they have completed their operations that was executing in epoch E-1. So that essentially means they have forgotten all the pointers once that operation in epoch E-1 complete and the threads move to epoch E. So that essentially means every thread that is executing in epoch E has forgotten all its private pointers that it was holding in epoch E-1. So that means in epoch E+1, any record that was retired in epoch E-1 could be freed safely because no thread holds a pointer to any record retired in epoch E-1. So this is how consensus is reached in EBR. Now let's see how it can be used. So we'll use the same lazy list update operation. So all you need to do is encapsulate a data structure operation within a start and end operation function, and you are done. So the repercussions of this way of arriving at a consensus on the desirable properties is as follows. So as far as speed is concerned, since EBR do not require per read overhead, they only have per operation overhead, where at the beginning of the operation they need to access a shared epoch variable, which is which each thread is required to announce, and periodically is also required to increment to announce a new epoch. And this can be actually amortized, and Deborah does this excellently. But the problem with this category of algorithms is that it is not robust, because the consensus depends on all the other threads to announce an epoch E. And if a thread if a thread never announces the current epoch, then no thread could advance the epochs, right? That means no thread could reclaim the retired buffers. That in turn implies that the number of retired records that remain unreclaimed in the retired buffers could grow unboundedly. As far as usability is concerned, as we saw in this lazy list update operation, so you just need to use start and end of operation, encapsulate your operation within these two functions, and you use retire function to send the node to be freed to be stored temporarily in the retired buffer of a thread. As far as applicability is concerned, EBR applied to all data structures which give you a guarantee that if a thread is not executing an operation, it is in a quiescent state. That means it won't hold any private pointer to a shared record when it is not executing an operation. So to summarize, consensus in HP is arrived because of this phenomenon that every thread needs to protect before it accesses and scan before it frees. And in EBR, every thread needs to wait for all other threads to arrive at a common epoch before the records retired in 2 epochs back could be freed. So this has an impact on the desirable properties of these reclamation algorithms. So because of the way they implement the consensus, epoch-based reclamation algorithms have high performance, as I said, because they have only minimal overhead, that too per operation. But the problem in them is they have unbounded garbage and they have high usability and applicability. But hazard pointer-based algorithms, on the other hand, because of per read overhead, have low performance. But the good thing is they have the bounded garbage. But problem is that they also have low usability and applicability. So it turns out that none of these algorithms completely satisfy all of these desirable properties. So this leads us to ask a question. Before we move forward, I wanted to make a point that in our paper, we also surveyed 18 data structures and we found that out of them, 15 to 15 hazard pointers do not apply. So for a comprehensive discussion on that, I refer you to read our paper. Now, so the important question which arises from this is that can we have a reclamation algorithm, a safe memory reclamation algorithm which satisfies all of these properties at the same time? That is, like, is robust, is usable, is fairly applicable, and is fast too. So the answer to this lies in thinking about the consensus in a different way. So we propose NBR, which is a different, which implements the consensus in an alternative way to and attempts to satisfy all of these desirable properties at the same time. So let's try to understand this consensus mechanism step by step and see what is the core of the neutralization-based reclamation algorithm, which solves, which addresses this important question of satisfying all the desired properties at the same time. So the core observation in consensus of NBR is that we free, so whenever a node is being freed, if somehow it could convey to other threads that it's going to free the node, so you guys should relinquish if you are accessing the node, if you are accessing them. So one way it could be done is like the other threads could restart, and in that process, they would give up the private pointers, and the thread which is trying to reclaim could safely free the nodes. So now let's try to apply this on these lazy list update operation, and let's see what happens. So this is a typical lazy list update operation. Now let's say some thread wants to free retired buffer, its retired buffer, and the other thread which might be holding a pointer to a record node in this retired buffer, let's say, is in the search phase of this lazy list update operation. Right. So if this green thread, which wants to retire the record, could somehow send a communication signal to this blue thread, then what it could do, since it hasn't done any updates in the data structure yet, it could simply restart. And doing that would be safe and correct because, as I said, it hasn't done any updates, right? So it could simply restart. But you may ask the question that it would give up its progress made so far. So wouldn't that be detrimental for the speed of the data structure when this way of arriving at consensus is applied? The answer is that the reclamation happens infrequently while the data structure is executing, right? So giving up progress once a while is fine, and that won't have that much impact on the progress, and that would be validated in the experiments when we reach to the experiments section of the presentation. So so far, forcing threads to restart while a thread is reclaiming the memory seems to work. But if that blue thread happens to be doing an update, then could we restart? The answer is no, because thread might have already done some partial changes in the shared memory. And if the thread now restarts, then it would break the correctness of the data structure. So how can we handle this? So it turns out that if we somehow can protect the nodes, that is present current nodes that would be required to be accessed, and tell the green thread which is trying to reclaim that skip freeing these records, then even though the blue thread will not restart, there would be a consensus between the two threads so that the use after free hazard will not occur. So let's see a complete picture now. So NBR actually sees a data structure operation consisting of different phases. So first, the search phase is referred to as a read phase, and the section in which the updates are done is referred to as write phase. So as we saw in the previous slides, a thread in read phase could simply restart, giving up all its pointers, so that a thread which is trying to reclaim memory could go ahead and free without worrying about any thread holding their pointers. And for a thread in write phase, if it somehow already protects the records it would need to access to carry out the update operation, then the thread which is trying to free a node would be assured that even though the thread in write phase would not give up its pointers, the thread which is trying to retire the records would make a concession that it will not free those records. So this is similar to what happens in hazard pointers where you protect. So in fact, you may now ask a question that since NBR assumes that data structure operation should be in this particular form where it consists of different phases, wouldn't it be hampering the applicability? Well, it turns out that most of the concurrent data structures have this property where long searches are followed by short updates. So they naturally have these phases in them. So NBR does apply to multiple data structures because of this predominant design pattern. Now, let's see at a high level overview how this consensus actually is realized or implemented in NBR. So let's say there's a thread T3 which is trying to free its buffer of retired records. So, and the other thread T1 is in read phase and some thread T2 is in write phase. Now, when T3 wants to reclaim, it will first send signals to these threads. Let's say T3 sends signal to thread T1, which is our neutralizing signal. Basically, these are the POSIX signals which T3 sends. And then when T1 receives this communication in form of this neutralizing signal, it will, in response, restart its operation, which implies that it will discard all its pointers. So T3 can simply be assured that T1 will not be holding any pointer in its retired buffer. So T3 can go ahead and reclaim its retired records. So this is a kind of a reader-reclaimer handshake that happens. Now, T3 then sends signal to the other thread T2, which is in write phase. Now, when T2 receives this POSIX signal, it would, since it is in write phase, it would have already reserved its pointer. So it will give a guarantee to T3 that it will not, even though T2 will not restart, but it has the records it needs protected. So that T3 in return would guarantee T2 that, all right, okay, even if you do not restart, you do not give up your pointers, but you have saved them, so I will respect those reservations or protections, and I will skip freeing them, and I'll free other unreserved records. So this is a kind of a writer-reclaimer handshake. So these two handshakes together help NBR to implement this consensus where use after free hazard is avoided. Now let's move towards the now let's see how we can use NBR in a data structure operation. So we will use we will again you make use of lazy list operation. So all one needs to do is to identify the read and write phase in a data structure operation and ensure that before beginning of the write phase, the number of records that would be required to carry out the updates in the write phase can be known beforehand. So let's see this in the same lazy list update operation. So here you invoke begin read function before you begin your read phase. And once your read phase ends and before starting the write phase, you call end read function. And this end read function also takes the records which you discovered in the read phase and that will be required in a subsequent write phase. So these records are passed to end read so that they could be reserved. In addition, you invoke neutralization checkpoint before you call begin read phase function. So this neutralization checkpoint actually implements the restarting behavior for the threads in the read phase. So this neutralization checkpoint is nothing but a call to zigzag jump, which saves the context of a thread in terms of stack pointer, frame pointer, and which could be restored if required, if a thread is required to restart. So let's say a thread executes this neutralization checkpoint and goes ahead to either execute read phase or the write phase, and if some thread wants to reclaim its record, it will send a neutralizing signal. So the other threads could, when they receive the signal, will execute a signal handler. And if the thread that executes the signal handler happens to be in the read phase, it will restart. So this restartable variable decides whether a thread is in read phase or not. If restartable is true, that means a thread is in read phase and it will restart. So the way that a thread restarts in read phase is by executing this sig long jump call. So whenever a thread executes the sig long jump call in the signal handler, it actually restores the context which was saved while executing the first zigzag jump call. Right? So it will behave as if it never executed in the read phase. And that way it will implement the restarting behavior. Now, if a thread happens to be in the write phase, it would be non-restartable, and it would simply return from the signal handler and resume what it was doing in the write phase. So let's jump deeper into the implementation of NBR. So first, let's see the metadata which NBR maintains. So each thread has a logical thread ID, which is this TID. And then every thread also maintains a private buffer, which we call limbo bag here. And each thread also has this restartable variable, which tells whether the thread is in read phase or write phase. That means if the restartable is true, that implies that thread is in read phase. And if restartable is false, that implies the thread is in write phase. And each thread also maintains a tail variable, which points to a retired record, last retired record in the thread's limbo bag. Also, each thread maintains our single writer multi-reader locations where the records that needs to be preserved or reserved before entering the write phase are saved, so that any thread which is trying to free the nodes could scan these reservations and skip freeing them. So in begin read phase function, you first clear your reservations from the previous operations, and then you cast restartable to true. At this point, you may ask that since that if restartable is a local variable, why do we need a cast? Well, that's important because we want to avoid reordering of the instructions in the read phase with the execution of the begin read function. And in end read phase function, you actually pass the records which you have discovered in the read phase and which are required to be protected so that the subsequent write or write phase could be executed. Right. So so you preserve those records and then you execute a cast to set restartable to false. That means you set restartable to false. That means whenever it is a signal, it won't restart. Now, the retire function is the one where all the meat lies. Here, you first check whether your limbo bag has reached to the full capacity or not. And if limbo bag is completely full, you start sending signal to all the other threads. And when you finish sending signals, you, by the virtue of the handshakes, you get a guarantee that all threads would have either discarded their pointers or would have reserved them if they haven't discarded those pointers, so that you can go ahead and reclaim the records by skipping any reserved nodes or records and empty your limbo bag. And after that, you can simply add the current record which you want to retire in the limbo bag. Now, moving towards some precautions one needs to exercise while using the NBR interface. So these precautions actually stem from or arise from the standard restrictions which apply to any code which uses non-local jumps in terms of zigzag jump and SIG-set and SIG-long jump. So, as we know, NBR sees the data structure operation into different phases. So a thread is actually not allowed to access any shared record before executing the read phase, that is the pre-read phase. But it can access any global variable or can execute any system calls. Since in pre-read phase, any thread is guaranteed that it will not restart. So executing system calls or accessing or writing to global variables is safe. But accessing shared records is not safe because they are not preserved. And in read phase, access to shared or global variables is allowed, but writing to them is not allowed because a thread might restart. So writing could break the correctness. So as I said, standard restrictions of using non-local go-to jumps apply here as well, because NBR also uses non-local go-to jumps to implement the restarting behavior. And in write phase, access to global variables or doing system calls is permitted because a thread would, after receiving a signal, would not do a SIG-long jump. It would simply continue what it was doing. So using global variables or accessing them and calling system using system calls is permitted. And you can, in write phase, you can only access the records which are preserved, shared records which are preserved or reserved. So now let's see how NBR performs. It turns out that NBR performs comparable to state-of-the-art algorithms, but our aim here is to outperform best of the safe memory reclamation technique in the state-of-the-art. So with that aim in mind, we started thinking about improving the NBR, and we observed that the main overhead in NBR comes from the fact that every time a thread wants to reclaim its buffer override record, it has to send signals to all the other threads. And these signals are costly because they trigger page faults in the underlying operating system, and that adds up to the latency. So we started thinking of reducing the number of signals that are required to be sent in order to reclaim for threads to reclaim their retired buffers. And in that process, we designed NBR Plus, which is an optimization in terms that it reduces the number of signals which needs to be sent to reclaim buffers. And spoiler alert, it turns out that NBR Plus is approximately 2 times faster than plain NBR. NBR Plus is 2 times faster than plain NBR for large number of threads. So let's see how NBR Plus manages to improve over the performance of NBR and reduce the number of signals. So the key observation here is that in NBR Plus, actually, a thread can piggyback on another thread which is already sending signals to reclaim its own records, and thus need not send signals of its own. So let's see this through an example. How is that possible? So let's say a thread T1 has retired a record R at this point, and later a thread T2, in order to reclaim its retired buffer or limbo bag, sends signals to all the other threads. So let's say it starts sending signal at time t and finishes sending signals at time t prime. Now, when these signals are sent, by virtue of reader reclaimer and writer reclaimer handshake, it is guaranteed that every thread would either restart, or if it not restart, it would reserve its pointer. So that implies that every thread after time t prime would either discard its pointer to the record R, which was retired before time t, or would have it reserved in its reservations. So that means T1 can free this record R if it is not reserved after time t prime. So this tells us that if T1 can somehow observe this time interval t and t prime, where thread T2 has started and finished sending signals, then it can reclaim some of its records in its private buffer without sending signals of its own. So this is how one thread can piggyback on another and reduce the number of signals which are required to be sent. So let's jump into the implementation details here. So the way we implement this piggybacking mechanism in NBR Plus is that each thread maintains 2 thresholds in the bag sizes. One is high watermark, where a thread reclaims as it does in NBR by just sending signals. But we might also maintain a lower threshold, so where a thread, if it enters into that lower capacity threshold in the bag, we call it low water mark, then it starts observing for a piggybacking opportunity and starts monitoring for a thread that might be sending signals already. And if it successfully observes that interval t and t prime, then the thread could reclaim some of its record at low water mark without reaching at high water mark and sending signals. So now let's see the pseudocode of the NVR Plus's implementation. So the only difference here is that we need extra metadata to implement the piggybacking mechanism here. So each thread maintains a scan TS, that is the array of the array of timestamps recorded for every thread, and so a thread saves the timestamp of all the other threads so that it can be compared later with the current timestamp of other threads, and a thread could realize that that some thread has started and finished sending signals. And in addition, a thread maintains a low watermark entry flag, which helps a thread to create some metadata the first time it enters into the low watermark entry. And a thread also maintains a pointer to the last record that was retired in its private buffer, so that it keeps track of till what point it is safe to free a record before it observed a successful before it has successfully observed another thread which has started and finished sending signals. And a thread also maintains a single item multi-reader location, which is announced TS, where a thread announces its timestamps when it is actually sending signals. So in this way, a thread which is sending signal can communicate to other thread which is looking, which is trying to observe a thread which might be sending signals. So let's see how the retire is implemented in this case. So if a thread's private buffer is completely full, we say that it is at high water mark, and in that case, we simply reclaim as if we do in NBR. That is, we simply signal all the other threads and then reclaim the unreserved records. In addition to that, a thread to communicate to another thread which might be at low water mark looking up for a piggybacking opportunity, it communicates that it is sending signals by incrementing its single item multi-reader timestamp twice, once before sending signals and once after sending signals, so that a thread would know the time t and t prime, which corresponds to when a thread has started and when a thread has finished sending the signals, so that thread at low water mark looking for the piggybacking opportunity could reclaim its own buffer as well. Now, thread before sending signals of its own, that is before reaching high water mark, hits the low water mark first, right? So the very first time it enters into the low water mark, it will record some metadata. So the first is it records the pointer to the last record it was that was retired before this thread entered the low water mark. So that would be the point up to which, if this thread in future happens to observe a successfully observe a thread sending signals, till that point in its retired buffer, it would safely reclaim the records. And in addition, this thread which enters the has entered the low water mark will save the current timestamps, announced timestamps of all the other threads, which would later be compared with the current announced timestamps to realize that time t and t prime has occurred. So after recording this metadata for the first time when the thread enters the low water mark, in the subsequent retired operations, the thread actually observes or reads the announced timestamps, and if it sees that some thread has incremented its timestamp twice since the time it saved the timestamp when it first entered the low water mark, then it could safely free its records up till the recorded bookmark tail. And then the thread could clean up the metadata and so that it could prepare itself again for the next time it enters the low water mark and can reclaim without sending signals. Now let's move on towards the evaluation of NBR. So we experiment on a four socket machine, Intel Xeon machine, which has 192 hardware threads, and the operating system we use is 1218 with O3 optimization flag enabled. So so we do multiple trials. We collect stats with multiple trials, and each trial is of 5 seconds each. And the data structure which we used were binary search tree, AB tree, and binary search tree by DGT and AB tree by Brown, and lazy list and Harris-Michael list. So in this presentation, we'll only discuss the performance with binary search tree and AB tree, and the performance evaluation with lazy list and Harris-Michael list appears in the paper. So the state-of-the-art algorithms which we compare against is Debra, which to best of our knowledge is the fastest known EBR variant, hazard pointers, and then interval-based reclamation algorithm, question state-based reclamation algorithm, and RCU. So the first plot shows the comparison of external binary search tree, and it is for a workload of 100% updates, and the tree size is 2 million. The x-axis here shows the number of threads, and y-axis shows the throughput, that is million of operations completed per second. The top dashed trend shows the performance of the data structure without any reclamation, and it serves as a reference point as to see how much overhead does the reclamation technique add to the data structure. So as it can be seen here, NBR plus actually outperforms hazard pointer, IBR, RCU, QSBR across all the threads and even under oversubscription. One interesting point to be noted here is that NBR plus outperforms Debra only after 96 threads. Before that, Debra plus is actually marginally better. And this can be attributed to the fact that Debra plus suffers from delayed thread phenomenon. So since threads could get delayed, that means consensus could get delayed, and that means the limbo bags of every thread could keep on accumulating retired records, and so they get very large. And once the limbo bags actually eventually get to free themselves when the consensus happens, that actually this burst of freeing that happens actually bottlenecks the underlying allocator. So this overhead actually increases with increasing rate of updates and increasing number of threads, because then only the buffers get filled up with higher rate and when they and actually can bottleneck the underlying allocator. So in this case, the crossover point occurs for 96 threads, because at that point, the pathology due to delayed threads sets in. Now, for more realistic workloads, that is 50% updates and the size of tree 2 million, we observe that again, NBR plus is better than hazard pointer, QSBR, RCU, and IBR for across all the threads. And this time, in comparison to Debra, the crossover point occurs much later, which is at 126 threads. And the reason is that the buffers get, due to a low number of updates, that is 50%, buffers get filled up slowly, and therefore they can only manage to become huge enough at when number of threads are 126 around. So at that point, this bottlenecking phenomenon of the underlying allocator sets in. Now, for even more realistic workloads, that is only 10% updates, here again, NBR plus outperforms the other algorithms. But an interesting comparison is again with Debra here, where the crossover point occurs now much later, which is again due to the similar reason that the rate at which the buffers get filled is slow due to the low number of updates, and the bottlenecking of the underlying allocator only sets in at 192 threads. So one thing is common, that NBR plus has outperformed all the other algorithms for a large number of threads. Now, comparing NBR plus on Brown's AB tree, one thing point to be noted here is that we do not compare it with hazard pointers and other recapture techniques, is that NBR is that Brown's A-B tree is not applicable to hazard pointers. As we said, as we have seen that hazard pointers don't apply some data structures where a sequence of logically related nodes could be traversed. So hazard pointers in this case do not apply to Brown's A-B tree. So we thought of only comparing it with Debra, which to best of our knowledge is the fastest known safe memory reclamation algorithm. So here again, we see that NBR plus outperforms for a large number of threads, especially after 96 threads. And before that, Debra is better. And this crossover is due to the fact that delayed threads in Debra actually leads to bottlenecking of the underlying allocator. And for 50% updates here, now again, the trend is similar. NBR plus maintains its upward trajectory for a large number of threads, and Debra tanks down for a large number of threads here, and the crossover point occurs much later because of reduced number of updates. And for 10% updates, again, NBR plus maintains its performance trend, but Debra tanks down for a large number of threads, especially after 192 threads where the bottlenecking phenomenon sets in. So in conclusion, we have seen that if we design our consensus mechanism in SMR carefully, we can manage to attain all of the desirable properties. So NBR plus actually is faster and bounds the garbage, is fairly usable, and applies to multiple data structures. As far as applicability is concerned, there are some data structures to which NBR may not apply. We discussed that in length in our paper. So we refer you to read our paper for that. So there are some things which I have not covered in this presentation is the survey of the data structures to which NBR plus and hazard pointers do not apply, and additional experiments with like arithmetical list and lazy list, and the discussion on generalizing NBR to complex data structures to which NBR may not apply as it is. So all that appears in our technical report at archive, and you can also see we have a code available on GitLab. Thank you and good luck.